Hi. This video is just going to be a little look at the loader of the Ultimate 1 megabyte and Incognito firmware, which I started working on a couple of years ago, and it's been quite well received. But the past couple of evenings, I've been working on the loader, a little update to the loader, and this loader runs on the Ultimate 1 megabyte, the Incognito and the side cartridge, and it is available as a standalone executable as well. So there's 4 different sort of builds of this loader that you can use. So I thought it might be interesting to have a little look at how it was possible to add additional features to this loader when I'd basically completely run out of space. So to give you a little bit of background, that's just my coffee cup bumping off the mic, excuse me. To give you a little background on this, the loader runs out of a 16K ROM. It's 2 8K banks of ROM that act basically like a cartridge. In the case of the Ultimate 1 megabyte Incognito and side cartridge, so it occupies 2 8K banks. So you've got an interbank calling mechanism, so that code in the first bank can call code in the second bank, which in turn can call code in the first bank. So you can go backwards and forwards with GSR, jump to subroutine, to a nesting level of about 8 or something. And there was various ways to do that. What I opted for, if I can find the macro file here, I think this is something I first figured out when I was working on the PBI BIOS. I can't even remember which one I'm using here. This must be it. LGSR code. Yeah, that's it. Yeah, right here. This must be it. Right, so here we are. LGSR code. So this code is placed. What address is it placed at? I don't remember. The ROM should be in here. Right. So here we go. This is the end of the first bank. So that's it there. So that's the code that jumps between, or GSRs between one bank and another. It's about 70 bytes long or something, by the look of it. So it goes at that'll be BFB8. That would be the address. So that goes at the end of bank 1 and in the end of bank 2 as well. Here's exactly the same thing. So the idea of this is that the code is identical in both banks. So what you do is, I'll find an example of the macro call. So the macro call is called LGSR. This is the MADS assembler, by the way, and you'll see that we're working with the Woodson IDE. So this is the LGSR macro. The colon is used by the MADS assembler to access labels that are outside the current bank, because we've got the 2 banks of code cordoned off from one another somewhere. I should be able to have a look, because we've got next bank, the next bank macro. So this appears at the end of the first bank, and it does it bump the bank number? Yeah, there we go. NMB. So that's next memory bank. I think that sudo op means next memory bank. So the internal bank counter of the assembler is bumped to the next bank. So that sort of cordons off, localizes the scope of the labels in the first bank and the labels in the second bank. So to access one label from the other bank, you need to put a colon in front of it, which gives you sort of global access. I'm not sure if I'm using the proper terminology here, I rarely do. It's probably called something clever like a scope modifier or something. But anyway, so LJSR reset drive, for example. So this resets the IDE controller. So that inserts this macro LJSR. Now, let's ignore this exe part. If that means if, let's think, I'm trying to remember how this works. Right, if parameter 1, which is the argument, which is reset drive, okay, if reset drive equals this, right, now this is a label inside of the macro. So if the bank number, because the equals colon is a way of, it's the operator for the bank number of the label. So if the bank number of the target label is the same as the bank number of this label, then we just JSR, because we know that the target is in the same bank as where we're calling from. Otherwise, we JSR to the long JSR code, and we've got inline arguments. And the inline argument is the target bank plus the base bank, because the bank that this code is assembled to isn't always bank 0 and bank 1 or whatever. So there's an offset. So the target bank plus the base offset, and then we've got the address, the actual value of the label. So this calls that code that is static, that is present at the top of each bank, pulls the arguments, the inline arguments, and does a lot of stuff. It's a little bit long-winded, but they're not really time critical. The main concern was to preserve, not so much preserving registers on the way in, but preserving registers on the way out. So what basically happens here is we get the low byte of the return address off the stack, we skip over the arguments, and then we push the return address back. The return address, which is pushed, it skips over those inline arguments, so that's on the stack. And then, because we've set up these, we've set up this pointer, 0-page pointer, then we can pull those arguments that we've just skipped over. We can pull them out of memory, out of the, well, it's ROM, and set up the jump to the target, because obviously the target code's going to end in RTS, so we don't need to do a JSR, we can just jump into it, because we don't need any sort of dangling RTS otherwise. And this was kind of the reason. This is like the RTS trick where you push the target address on the stack and then do an RTS. Now the reason I've used RTI is because RTI, when it pulls the address off the stack, it doesn't add 1. It doesn't add 1, whereas RTS does. And there was some reason that it's expedient here to use RTI instead. So that's a nice little trick if you want to do the RTS trick. But for any reason it's not convenient to have 1 added to the address that you're pulling off the stack, you can use RTI. I think the reason, in this case it doesn't make any difference. I could have just put -1 here to drop the return address and then done RTS here, and the effect would have been identical. I'm not entirely sure why I've done it that way. Now, so that jumps into the target code. Now when the target code reaches RTS, the address of this routine is pulled off the stack, and we come here. Now in this case it's particularly useful to use RTI because we're saving the processor status register here, pushing it on the stack, pulling it back off again, saving it, and then we're getting the saved bank, which is up this was the originating bank. We're pulling that off the stack, setting the bank, and then we're getting the flags back again, the processor flags back out of bank temp 1, pushing that on the stack, and then RTI pulls that off the stack again, and the processor status registers reflect what was on the stack. So I think this is, I realised that there was no need to restore the accumulator in the Y register here. But yeah, I'm a little bit unclear as to why I've done that way. So the key point here, bank is the hardware bank switching address of whatever device this is built to run on. Now as soon as that's written to, the bank changes, the ROM bank switches there and then. But because the code is the same in both banks, we don't crash, because when the moment that's written to and the next bank comes in, the code path is identical, so we just come back out. So that's quite useful. Coffee cup again. But anyway, I got a little bit sidetracked there. So what was I talking about? Bank switching, yeah. So that's how that works. So we can jump in between one bank and another without any problem. Some people ask about compiling ROMs with this assembler. I mean, there's a lot of conditional assembly stuff here. The opt-h minus, that suppresses the binary file header, the 6-byte binary file header, because we don't need this because this is a ROM. Other flags of interest, opt-f plus is a sort of a fill flag. So if you do a sort of a .ds, let's see, find some data. I think I've studiously avoided using .ds because for the precise reason that it does generate fill bytes. I mean, this is the equate file. Fill's turned off here, obviously, because this is just describing addresses. But if fill's enabled when you do a DS 1024 or whatever, you'll get 1024 zeros in the binary. And that's just if in the case of the ROM code, the code that runs in ROM, that's a complete waste of space. But for code, it's useful for alignment, because the where are we? Just undo that. The next bank macro that explicitly enables yeah, we're turning off fill. Yes, I can't remember why that works. Anyway, it works. There's so much experimentation went on to get these flags to work correctly. Because I was when I was first experimenting with them, you suddenly find you get 64k of padding or something between banks and unwelcome side effects like that. But anyway, it works. So yeah, so we've got two banks of code, and I've tried all sorts of because it's quite complicated, this loader, and it's dealing with a lot of 32-bit fat cluster numbers, and there's quite a lot goes on. So eventually, pretty quickly, everything was full. Both 8K banks were full of stuff, and quite a lot of stuff is bitmap data, because if we jump into the emulator here, I'll have to jump to the other monitor. Okay, and we go here. Alright, so if we jump into the emulator, the right, get rid of that. The file list where where you're going to spend most of your time is just one part of the loader. There's also a list of partitions. These are MBR partitions, so a mixture of FAT partitions and the APT, which is kind of the container, for want of a better word, for the Atari partitions. There's also a mount table. So there's just to get the volume label from a FAT volume. It can be stored in a couple of different places. It can be in the boot sector, or it can be a specific entry in the directory. And I found that when I was preparing media in a different operating system, like a Linux-based operating system, that the label was a completely different place to where it would be if you'd prepared it with Windows. So the loader has to decode both volume labels, one from the boot sector, one from the directory, and one supersedes the other. And eventually found a setup that seemed to work consistently. And it doesn't look like there's an awful lot going on, but there is a lot going on to extract all this information from the disk. So the code's as compact as I could make it. So recently what I wanted to do was a couple of things I wanted to change on the loader. I wanted the search facility. Previously, it only searched it searched from the beginning of the string, so it's a recursive search now. The previous big push to shrink the code down allowed me to add this recursive search, because the search facility used to just start to type, and the highlight bar would jump down to the first match. So it was more like a shortcut to the whichever point in the alphabetic list. Just by you would start typing. Say if you'd start typing B-O, it would alight on bomb jack, and as you type more characters and sort of disambiguated the string, it would narrow down to the target. But that was kind of useful, but it could have been better. So what I decided to add was a recursive search. So if we find something to look for, yeah, so if we go into, we can just start typing C now, and then to look for chess, and eventually it finds chess ROM. Now chess ROM was in the ROM folder, so it's recursively scanned the whole FAT directory tree and found this ROM, which you can then run. And if you want to find out where the matched file actually lives, you can press Ctrl F and it'll open the directory, the containing directory, and then you can see the file that you found, and you go back to the root. So that took quite a bit of space, and to find the space for all that stuff, it was getting pretty ugly what had to be done even then. Looking for bitmaps, shrinking things down, adjusting the playfield, because there was all this padding up here and up here in the bitmap, so the playfield got shrunk down. Or was it round the logo? I think it was round the logo. This had to stay full playfield width because of the bitmap includes the little curved detail parts at the side. So there was, anyway, I found some sort of inventive ways to shrink the code down, and somehow found the space to put all this stuff in. But we literally had 6 or a dozen free bytes in the ROM, so it was really hopeless trying to add anything else, and it got to the point where even prompts and information on the screen had to be as concise as possible, because the strings were taking up room, and it just fit. So what I wanted to do with this search facility was change it a little bit so that you could optionally match any character in the string rather than just searching from the beginning, so that, for example, if you type basic previously, it would just match any file name that began with the word basic. But optionally, I quite like that behavior because it's fast and it's simple, and it keeps the amount of search results. It keeps the length of the search results low, which is important because there's only room for 240 odd results in the list. But I wanted to add this optional behavior of it matching anywhere in the string, because the Robin Edwards loader for the Uno cart, he added a nice search facility to that menu, and that one works that way. It matches anywhere in the string, although in that case it's not the 6502 doing the search work and the string comparisons, it's actually an ARM processor. But still it worked well. So at the moment, in this test build of the loader, it should be switchable behavior. So I've added another option here, search start or anywhere, which I might have room to expand a little bit because it's not too descriptive. But that should be switchable. At the moment it's hard coded to anywhere, but I'll have to fix that up a little bit later on. So now if you type basic, it's searching anywhere in the string, so obviously it matches at basic, basic games, turbo basic and all that kind of stuff. And there was a few other things that takes a bit of space. There wasn't even room for this menu item, so I was stuck solid trying to find space for this stuff. So in desperation, I turned attention to bitmaps. Now the first thing that looked ripe for compression was this logo here. Now if you look at this logo, you can see that the most common repetition in this bitmap is going to be vertically. So if you read this bitmap in columns, top to bottom, left to right, you're going to get a lot of repeated runs of the same value. Not so much running right to left, left to right rather, not so much running line by line. You're not going to get much repetition there apart from here, but top to bottom you're going to get a lot of repetition. So it seemed to me that the best way to compress this data was to run length encoded, but do so top to bottom and then left to right. So I cobbled together I was going to write a tool in, an RLE tool in BASIC or C on the PC, like a little command line tool, but alarmingly, and this is just weird the way my mind works, it was easier to write it in 6502. Almost anything I want to do is easier to write in 6502 for some reason. Well, it's probably the reason being that's just what I'm used to. That's how my mind works. So what I ended up doing was writing this thing. Well, it wasn't actually this one. It looked very different. At first I wrote this RLE tool, a compressor, and it read the file, it read the bitmap file from the resource folder. Oh, I'm on the wrong view here, I'm going to put you on the right desktop. So this RLE tool here, and originally it read the bitmap file in, and then it reorganized it into sort of columnar format, and then it ran through this RLE compression code and spat the RLE encoded file out the other end. Now the problem with this is that when you come to the decoder, because RLE decoders are very, very, very simple, but because the RLE encoded data to make the most of the repetition running down over it, when it was decoded, it also had to be decoded in columnar format. Now that is not so cheap. It's not quite so easy, the code to decode the compressed data was a little bit, it's going to be more complicated than just doing a standard left to right, top to bottom decoding. So I gave up on that one, and actually the RLE encoded data wasn't dramatically smaller than the raw data, which I found a little bit surprising actually, but yeah, it wasn't. And then I would have had to have a table of lines, and I gave up on that idea. Wasn't ideal. And if you just encoded it left to right as a stream, it actually got bigger. So that logo, without doing something clever with it, was not a good candidate for RLE compression. So the next thing I turned my attention to was the icons. Now this is a 40 byte by 20 something lines of 1-bit bitmap data. So I ran that through this RLE encoder, and the file shrunk to about 2/3 of its original size once I'd tweaked this encoder, which it's just a mess. I'll get into that in a minute. But yeah, saved about a couple of 100 bytes, and I thought, well, this is good. And then I thought, well, what else can we run through the encoder? Well, I ran the font through the encoder as well. So this font is run length encoded, and I'd already manually described these repeated bitmaps, these little corner pieces and whatnot. They were already run length encoded, so but they had a special sort of bespoke mini decoder when the program set itself up. That, in fact, that was where I think that was where I got most of the additional space for the search facility, was encoding these little 40 byte bitmaps. Because added together they came to a couple of 100 bytes or so, and that was enough. With a few other things, that was enough to add more stuff, but we used up that room. So these little bitmaps, 6 or 7 of them, they were already encoded RLE, so I just got rid of the little bespoke encoder and let the main decoder run through that, so that you get the icon bitmaps, the font, and those little bitmaps, excuse me, and they get decoded on the fly when the program starts up, and copied from ROM into RAM, decoded from ROM into RAM. Once again, I'm on the wrong camera, the wrong view. Okay, so these little, I'm talking about these little bitmaps here, these 40 byte bitmaps, they were run length encoded previously manually by hand because they were so simple. So now we've got this bitmap here, these bitmaps, top, bottom, and the font all went through the run length encoder, and it gave me about 300 bytes of extra space to add stuff. So if we look in if we go to the hex editor, I should have a keyboard shortcut for this. If we go into hex editor, so this is the loader ROM. So here we've got all this free space, still nearly a page of free space at the back of the second bank, which is brilliant. And this run length encoder, this is just this is one of those things that if you look at some bitmap data, let's have a look so we can find some. Yeah, right. Here's the font. This is the original font data, and this is the compressed font data. So the format that I wanted the RLE data in was a control byte. This is the first control byte. Now a control byte with bit 7 set means that what follows are n repetitions of the following byte, and a control byte with bit 7 clear means that there are what follows is a literal stream of n bytes of data. And the reason I haven't used n minus 1 here, which I could have done, is because I wanted the length 0 to mean end of stream. Okay, so each block is limited to 127 bytes because it's described in 7 bytes. If that's exhausted, then just a new block starts. Okay, so that's what I wanted, and I looked online for a tool that would actually take this data and spit it out in this format, and I couldn't find one. So I wrote one, and I completely overcomplicated it. Because RLE compression is just dead simple, but it has to do look ahead, and I didn't want, because what you can end up with, what I did end up with initially, before I bodged it, was say this. Let's have a look. See what we don't want. Okay, so see here we've got 2 hex 32s, one next to another, and they are right in the middle of what is obviously an uncompressible. Well, at least not for RLE. It's an uncompressible stream of literal bytes. Okay. So what we don't want the compressor to do is it's scanning through, and it's, say, back here. How far back do we have to go? Say about here. That's probably where it started. So it started a literal stream of bytes here, which didn't bother to try and compress because there's nothing repeated. Oh, here. This is a better example. Here we've got 99 repeated. So I think we had 4 F3s, and then we had 7F or FF C3. There's nothing repeated there. So the encoder is busy encoding a stream of literal bytes. So the control byte will be right here, and it's scanning through, and it's not seeing any repetition. So it's bumping a counter here to describe how long this block's going to be, and then it hits these two. Well, what you don't want to do is break that stream, end that block, and then tell it to repeat 99 twice, because it doesn't make it any smaller, because you still got 2 bytes, and B, it's broken the literal block unnecessarily. So this literal block, unless there's a good reason to do so, i.e. a byte is repeated more than twice, at least I would say, you don't really want to, want to interrupt it. So I had to bodge this thing here. Where are we? It's down here. I think it's down here somewhere. Where is it? Yeah, it does. It scans ahead again. So this is where we're doing a literal block. So we get the next byte from the stream compared to the previous byte. If it's the same, we jump here because we're expecting it to be different. So if it's the same, we go here, and then we jump ahead a little bit more, and we check the third character, if you like, the second. We look ahead twice, 2 positions, and we compare that one again. So if the repeated data isn't, at least if it doesn't repeat 3 times, it doesn't break this literal block. So that's how it works anyway. So we can see how it works. We've got the control byte 89. That means that 0 is repeated 9 times, and which it is there. And we've got the next control byte is a 2. Bit 7 is clear. That means we've got 2 literal bytes following. So that's 7F and CO. And then the next one is 84, which means we've got a repetition of 4 repetitions of F3, which is what we've got there. And then we've got how many is that? 24, 36 bytes of uncompressed data. And there we go. And then we've got 3 repetitions of CF, etc., etc., etc. So that, I mean, it hasn't shrunk massively, but it's smaller. It's sufficiently smaller, and bearing in mind that the decompressor for this is shared among other data, which did compress better, then pound for pound it's actually worth it. Okay, so and this tool here is so rough at the moment. What I'm actually doing is running it, breaking out of the emulator, and then just dumping it to disk, and then manually trimming it down. But as I say, I didn't want to spend ages perfecting a tool, an RLE tool, when all I wanted to do was compress 3 bits of data. So that works anyway. The decompressor, I mean, this is very, very primitive for anybody who's got any understanding of compression. This is just going to seem dead simple in the extreme. But anyway, here we go. So this is the part of the code in the loader which actually copies code and data from ROM into RAM, because the certain things need to run in RAM, bearing in mind we're bank switching all the time in the ROM part. So there's things like the interrupt handlers and stuff like that. Bits of text get copied into RAM. So here we come to the good bit. This is the decompressor for the RLE data, run length encoded stuff. So we've set the input pointer to the start of the data. We set the output pointer to the first destination address, which is the font. So the things come in the order of the font, the icons, and then these bitmaps. And they are all just one after another, with a terminator byte, a control byte, a terminator control byte at the end of the last stream. So this whole block here is compressed run length encoded data, which is going to line up perfectly when it's decoded. And we grab a byte, see if it's there's a reason for that, by the way. If you think I should, before you say, oh, you should have, why aren't you just doing BMI here? There's a reason for that. I'm not using BMI because the get byte routine clubbers the flags. So, where are we? Yeah, so if bit 7's set, we go here, and we mask out bit 7, and if it's 0, we're done. If it's not 0, we set up a counter and just repeatedly pull. This is to decode a literal stream, and we just repeat and loop around until we're done. And if bit 7 is set, if bit 7 is clear, sorry. Oh hell, I got that back to front. This is a repetition. Okay, so bit 7 was set here. We know that this is a repeated block, so we get the next byte, which we're going to repeat n times, and we just fill the destination buffer with that byte until the count at 0. Okay, so here bit 7 is clear, so this part is a literal run, so we just get and put until we exhaust the counter. So that's how it's decoded, and eventually with a lot of jiggling around, of moving stuff around, it all worked. And like I say, pound for pound, this code, how long is this code to decode the data? It's not much, 30 bytes or so, and it saves, it opened up a page of space in the code or something. So that's pretty much how that's how bad things are when you have to resort to this RLE compression just to find space for extra stuff in the code. Beyond that, I'm not sure what you could do. As I say, this get back into this. This logo at the top doesn't compress so well, and it needs a different kind of decoder if you compress it in columnar format. So I'm not sure where we could go from here, but there's still a bit of space left. If we go into the ROM, we've got how many? There we go. We've got a couple of 100 bytes left, so I think that'll be more than adequate. Say I'm on the wrong on the wrong view again. So if this is the ROM. We've got a couple of 100 bytes left. I think that's more than adequate to do everything we need to do. We can broaden those little prompts a little bit and make things a little nicer. For example, I'm on the wrong camera again. Okay. Yeah, so the search facility. Someone was saying, oh well, when I backspace over the search string and it's empty, why doesn't it come out of the search mode? Well, the reason for that is because if it did, it would start to reread the current directory in completion, and that can't be interrupted when you start typing. When you type in the search string, pressing a key actually interrupts it, restarts the search. Not so when it's reading the when it's not in search mode. Don't ask me why. I thought about changing it, but it got very complicated very quickly, and it wasn't a big deal as far as I was concerned. So the way that this works is, okay, you've typed the search string. There we are. So we backspace over the whole thing. Say you wanted to backspace over there and start a new search string. Well, I don't want the thing to be tied up reading a folder just because you've backspaced at the start of the string. So the user was kind of left hanging here, not knowing what was going on. Well, now I've got the space to... are we still on the right view? Yeah. And now I've finally had the space to put this in. You see something like that on a smartphone when you press the back button repeatedly, and sometimes some applications will say press back again to actually exit, just in case you made a mistake. So I've just followed suit here. So you've got this, when you backspace over the last character of the search string, it says press del or escape to cancel search, so you can press del again, and then you're back out of the search. Just little things like that to make the thing a little bit more usable, because I know nobody reads the manual. There are all sorts of things in here that are easy to miss if you didn't actually read the instructions. I showed you the folder, go to folder thing already. Other things like you can turn basic on and off. Well, I'm going to do a proper video about how to use this thing. It won't be very long, but since I've made some changes, I figure I might as well do a video that shows you some of the tricks you can use in here. So yeah, I don't know if that was interesting or not. Consumed a few hours of my time fiddling on with this stuff to just try and find different ways of finding space. I suppose it applies a bit more to ROM code than it does to applications which load straight into RAM, because when you think about it, well, the point is that, you know, once the RAM's full, it's full. This is filling RAM from a a fixed space of ROM. So the more we can pack in here, the better. I mean, short of that, you could. It's an interesting topic, compression, anyway. But short of that, you could probably pack this. You could run the whole thing through a packer. Or everything that's extracted into RAM through a packer, and then decode that when it loads up. But that I don't want to go too far down the rabbit hole with this thing. I think it's a game of diminishing returns. This loader, it does its job reasonably well. And just for the sake of wanting to add a few little bits of polish to it, I'm not going to go any further with this compression game. But yeah, it was quite interesting. It's quite nice to just get the thing working after sort of beating your head against a wall, trying to going through code, trying to think, oh well, how can I get rid of that I'm on the wrong camera again. Yeah. Going through code trying to think, how can I get rid of this jump instruction? Can I not, can I move report error so that this falls into it? Once you get into that territory, and that's how bugs are introduced as well. You start moving stuff around thinking, oh well, I've saved 3 bytes there, and then you've broken something without realizing it. So yeah, that's not good. So now it'd be a case of going back through this, looking for strings that look a little bit too terse, and expanding them a bit so things look a bit nicer, things are easy to understand. So yeah, I don't know, I don't know if it was any interest, but that's how I found extra space in the loader to add more stuff. So yeah, so I'll see you next time.